Hello. All right. So hello, welcome to a new video. Today we're gonna do this problem called count good nodes in binary tree. It is 1448 medium problem on LeetCode, and we're gonna solve it using my problem solving process. I already kind of in quotes, solve this problem, because I couldn't figure out how to do it. So I searched up a video, LeetCode, Larry, coding live with Larry. I forgot his name already. But yeah, so I watched their videos, and it kind of helped me out. So I'm just going to um, try to, I guess, regurgitate or reiterate what I've learned and with my own understanding of it. So like I get better with these problems because I guess so far my weakest parts of coding has been binary trees. Obviously there's like other stuff that like I'm weak at that I haven't learned, but so far from what I've learned so far, this is the weakest. I'm okay with linked lists. Linked lists are easy. But binary trees, it's like, I don't know. It's kind of hard for me. I guess I don't quite understand the patterns of a binary tree, but I want to try to understand it in my way, like how to code it, and like, cause I know there's like different ways to like solve a problem with recursion, and recursion for me has always been hard. So I guess doing this video will kind of help me think of it in my way, so I understand it better for myself. And I'm just recording it so I can keep myself accountable and stuff like that. And maybe some other people that might watch this also feel the same way. Probably like a small percentage, but like still like I just do it. All right, so let's solve it or solve it again. Oops, those are my notes. Oops. Okay, so all right, so given a binary tree root. Oops, let me just do this first. So let's go read the problem and make sure we read it good. So given a binary tree root, a node x in the tree is named good if the path from root to x, there are no nodes in the path with a value greater than x. So yeah. So basically, yeah. So before I just continue off of basically, just get the input and output. So the input's basically tree node. I name root, which is the root of the binary tree, and then our output's just going to be an integer of good nodes. Okay, and to note what is a good node. So what is a good node is a good question. In our own words, we must say a good node. Good node is equal to x, where good node is where root to x, there's no greater node value and path from root to x, right? So good node is x, and a good node is where root to x, there's no greater node value and path from root to x. All right, so that makes sense. So basically getting the max if good is equal to if x is max in path. Right, that makes sense to me. So I'll just go through an example for that. So example, a good node is basically where, like, okay, so let's take this Jamboard that I did before. So let me erase, not just make a new one. So here we have 1 and 2 and 3, but we have like a 0 right here. Okay. So in this case, a binary tree, we have our binary tree to look like this, where 1 points to the 2, 2 points to the 0, and 1 points to the 3, stuff like that, right? So a good node is when from root to x, or from root to the node that we want to check is a good node, is where x is the greater. So if we want to go from 1 to 0, we want to check if 0 is a good node, then we have to check if from the path there's no greater value than x. So from 1 and 2, then 0, right? Well, 0 is like not greater than 2, not greater than 1. So no, this is not a good node. Not a good node. But in the pathway from 1 to 2, 1 to 2, 2 is the max of 2 is the max between 1 and 2. So 2 is a good node. So that's what it means to be a good node. So it's basically in the path. But if we just go continue on and just make new stuff, like 5 and like 7, or this 2 points to this 5 points to the 7. We want to see if 1 to 7 or root to x, which is 1 to 7, is a good node, right? So we have 1 2 5 7. If we compare all the nodes, basically compared to 7, 7 is the max, so it is technically a good node to the definition, of which root to x, which is 7, is that x is the max of the whole path we've taken, right? So yeah, yeah, that's a good example, I guess. All right. Anyways, so now that I've gone through an example, let's go ahead and possibly like ask some questions. So one question is like, what's the max? Oh no, what's the min number of nodes in input? We can check. It's 0. All right, and that's 1. Oops, 1. And then I guess this isn't a question that I brought up myself, but it's good since I've been asked that. So what's the min value of a node? The min value is 10 to the 4th negative, of course, so that's a good thing to note. Negative infinity, I guess. So that's good to note. Just in code, for code's sake. So now that we've gone through the input and output, we took some notes, we do understand what a good node is, and we've shown that through an example. We asked some questions that kind of clarify what is needed in the code. Let's go ahead and kind of match on what tools we can use to solve this problem. So in binary trees, I've mentioned this at the beginning, we're going to do some recursive stuff, so recursive functions, and we're obviously going to, with recursion, we're going to do some depth first search, and then we can also have some if statements, such as like if node is none or null, null node, and so on. Yeah, and what I'm thinking about is that we're gonna have a counter, because if this was like a list, we would obviously have a counter, or list node, or I mean a linked list or whatever. We would have a counter for this either way. So we're gonna have a counter to count good nodes, right? And yeah, so, and with recursive functions in a binary tree, we're obviously going to go through left and right of the nodes. So yeah, let's go ahead and plan. But before we plan, I just want to go through my driver code first. So main, we're going to run main, and then we're going to create a function to solve this problem. So I guess get good nodes, take in root, and it's going to make our tree node. And then I guess like left. Okay. Now let's go ahead and kind of, I think I like this example. Let's make this our example. So I guess we should have like 1, 2, and 3 good nodes, because the root's technically a good node, because the path from 1 to 1 is the max is just 1. So right. And then I think we'll get into the technicalities of like what we're going to do once we kind of go into the planning, but now I'm just kind of making our driver code. So I'm just gonna make our driver test case. So right, cool. So, and then in the driver code, we're going to print out the return value of get good nodes with the argument of root, and then we should return um the the top. I need a oh my god, I need it. All right, I just have to cough. I need to speak slower because my throat is getting dry and like I'm running out of breath because I'm speaking too fast and not breathing in. So let's practice that for future interviews because I would hate to cough in an interview. That would be kind of awkward. It would be awkward to just be like, damn, he's just coughing. I don't know. But anyways, so yeah, let's go through some pseudocode of it with my planning. So first thing I want to do is to kind of go through an example again, like how would we do this, right? So obviously when we start in a binary tree, we start from the root and then we go to the bottom, and then once we get the results at the bottom, we go back up to the top. So that's a good thing to note. We start from the top, go to the bottom, then return to the top. So start from bottom, we'll start from top, and then go to bottom, or leaf, and then go back up to top. So this is initial. This is basically iterating the first search, and then this is the result, turning result from initial call. So since we're going to start from the top and go back up to the top to return our result, we can obviously say return that first search, right? And then we're going to call that first search on the root. Right, that's what we're doing. And then we're going to use like a function, that first search, to kind of iterate through the binary tree itself. So this is kind of our blueprint. And then I guess the second part is that we go to the bottom. We're going to iterate through that first search. So when I say we go to the bottom, we're going to reach a point where we can't go any further. So that means like if not root, then return something, right? Return none or 0. But in this case, we want to regurgitate information back up to the top. So I guess in this case, once we reach like a null, basically, we're going to return 0, right? Because we want to count if it is a good node or not. So instead of returning none, let's go return 0. There's a better way to... I'm pretty sure there's definitely a better way to like kind of explain that. But that makes sense to me because I'm trying to notice a pattern, which is hard for me. So if we're trying to regurgitate information back up to the top, then that makes sense that we just do that, right? We return 0 if it's null, right? But we also want to kind of... If we also want to like, what do we want to do? We kind of want to return, in this case, we want to return like a counter. So in a way, we have a counter in the depth first search where we're counting the good nodes that we have right now. So good nodes is technically 0, right? So I guess once you start from the top, where you get this 1, and then we're like, okay, so if not root, then return 0, but that's not the case. So we have to call that first search on the left and the right. Oops, node dot left, and then that first search on node. Oops, let's name this node. And then node dot right, and then we have to do something there, right? Because it makes sense we do this. And then, so in this case, if we start from the 0, we're getting our information, right? 0, it returns, it gets 0 from both left and right. So in order to get that information back to the up to the 2, we gotta return good nodes up to the 2, right? That makes sense, right? And so now we kind of have like the base information, but now we just kind of have to work it in this problem sense, right? So again, in this problem, we want to detect how many good nodes are in the binary tree. And so good node is where the root to x, there's no greater node value in the path. So in a way, we kind of have to save what the current max is in the path we're going to. So instead of just getting the root, or instead of just getting a node, we also have to get the cur max, because that makes sense for this problem specifically. Because we can say that, okay, we start at 1, so 1's the cur max, then we got at 2, 2's the cur max, and then at this node we're like, okay, so the cur max is 2 in this path so far. And so I guess we can say that we had to compare the max. So cur max is either the max of cur max or the node value that we're at right now. This is kind of like pre-order, where we visit the node first, then go through its left and right. But yeah, this is pre-order traversal. So yeah, in this case, we have to visit 1 first, because it's the root. Yeah, then I think here we say that we have our infinity to be 10 to the 20th, because that's our infinity. So yeah, we have to kind of start at negative infinity, because we don't know if any node in the path could be negative infinity, right? So we just have to start at negative infinity, I guess. So in the case where we go down, so we start at 1, and then we compare, is the max negative infinity or 1, right? So we go with 1, and then yeah, and then in that case we say that if cur max, if node.val is more than equal to is more than equal to the cur max, then we're going to say that good nodes gets incremented once, because that means that if the cur max in the path that we're at right now is less than the node.val, that means that the current node is a good node, because yeah, it's greater than the one that we've had so far on the path. Yeah, which is basically root to x. So yeah, and then okay, we're kind of working like really the path I'm working to solve this problem is very all over the place. That's because I'm trying to like cover parts which I don't understand and trying to make sense in the time of the moment. So yeah, my apologies if everything seems like kind of off-putting or like out of order. All right, so back to this point. We're back to the subtree, right? So we said that when we reach the 0, we're going to return 0 in these cases, right? Mostly because it says if not root, then return 0. Then in this case, this zero says cur max is equal to the max of 2 or 0, and then we're going to call this, which we get 0, and then we're going to return good nodes, right? So in this case, good nodes will be 0 in this case, because we don't go through this case where the node val is more than equal to the cur max, because cur max is 2. And so 2 is going to get So 2 is going to get it's going to get its good nodes equal to 1 because it's more than the current max, which is 1, right? And so I guess in this case that we need to, once we're back at the 1, we have the information where or we can just collect it. So to collect the information, we just say that good nodes is equal to, is plus equal to DFS at the left, because we kind of want to say that information because we're gonna regurgitate it back. So it is, so initially 1 has good nodes equal to 1, and then we go down to 2, and then it says, okay, so plus 1, right? Then it has to go to 0 and check it, right? So that's why we say when we're back at this 1, good nodes plus equal to DFS at left, because we return our good nodes anyways. So good nodes is equal plus equal to on the right as well. So that should work too. So to run it down, let's go run it down again. I mean, it's just better to just write it again. So 1, 2, 3, then I guess like 0. So we have 1 pointing to 2, 1 pointing to 3, then 2 pointing to 0, right? And so this should work. I mean, just go run it. It should be like, oops, I forgot to cur max. Oops, what? Okay. It should have been 3. Yeah, because 1, 2, 3. Okay, cool. Let's just do it again with the code itself. So we're doing pre-order. So we're going to access the node first, and then we're going to go through its left and right. So, all right, so we start at the root, and we give it the root and the max of -infinity. And so start here. And then b is equal to 0. And so if not null, return 0. But in this case, it's not null. But we then say if no.val is more than equal to the current max, which is -infinity. So 1 equal to -infinity. That's true. So a good node gets plus equal to 1. So this is a good node. So that's 1. So I just say, 1. And then we say that the current max is equal to the, which is equal to the current max, which is -infinity, or 1. And then in that point, the current max is now 1. So current max equal to 1. All right. And now we send and now we call depth first search on node.left, and we give it the current max. All right, so on node.left, we go back up here. Good node is equal to 0. If not node, then return 0, but that's not the case. So if 2 more than equal to current max, which is 1, then increment good nodes, so it is a good node. Right? And then we update the max to 2. So max equal to 2. Right, and now we go to the left. So go to the left, we get 0, and then we check if it's a good node or not. No, but before that we say we check if it's null, it's not null. Check if it's greater than the max, which is 2, that's false. So we don't increment the good nodes. And then we either do not or do not update. Max is still 2. So I just kind of copy and paste it. And then we check it for its left and right. Right? And then we're obviously going to return 0 for both because they're none. And so we're on the 0 still. Good nodes get plus equal to 0 plus equal to 0. And then we return good nodes of this point. So good nodes at this point is 0, right? No, good nodes at this point is 0. So 0, 0. So 0 plus 0. Yeah, it's 0 still. And then now we go back up to the left. And it's 0. Oh, it's 1. Oops, 1. And then plus 0. Plus 0 and plus 0 because we have this empty, right? Then we go back up. So 1 plus 0 plus 0. I mean, this 1 goes back up to this 1 in this case because we got the left, right? So good nodes is plus 1 so far. Then we go to the right. Go to the right in this case for the root. And then we check if not node return 0, but that's not the case. Then we have to check the node value. So if the node value is more than the current max, in this case the current max is still 1. So 3 is greater than 1, so we say that this is a good node, so this is 1. Then we go through it to left and right. This 3 is left and right. They're both 0. 0, 0, return that back up, left and right. And then we return it back up to here. Good nodes is still 1 because 1 plus 0 plus 0 is still 1. Then we return good nodes back up here, up to this case, where we return the 1 back. So this one. Now we have 1 plus 1 plus 1, and we return 3. So yeah. It's kind of a handful, but we worked through that example, so it should work, which it did work. Let's go copy and paste it in LeetCode and see what it does. It should work because this is literally the same exact solution. Okay, cool. And boom, yeah, it's done. Let's review its complexities. For time, it's O of n. Because we're going through each node once due to depth first search. Then for space complexity, I'm pretty sure the space complexity, extra space, I'm not sure actually. I'm pretty sure it's just like O of 1 extra space because we're just using variables to kind of solve this problem. I mean, like, good nodes to solve this problem, so I think that's with the space complexity. But in general, we're using O of n space or O of h space, depending on the tree, I guess. I don't know. So yeah.